Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
So the chemical shift of a signal in the proton NMR spectrum can give valuable information about the type of hydrogens that give rise to that signal. So this is a typical correlation table that you should find in your textbooks that shows the average values of chemical shifts of representative types of hydrogens. Now these values are approximate, and other atoms or groups in the molecules can cause signals to appear outside of these ranges. But this will be a good reference to you. As you can see on the bottom right hand side at 0 ppm, that's our TMS, our reference, and then a variety of hydrogens attached to different functional groups at varying chemical shifts values. And so you'll use a chart like this or this information to solve NMR spectral problems. Now the chemical shift as shown on the previous chart of a particular type of hydrogen depends primarily on the extent of shielding that it experiences. And this shielding in turn depends on three factors. The first is the electronegativity of nearby atoms. The next is hybridization of adjacent atoms. And the third is the magnetic induction within an adjacent pi bond or other diamagnetic effects. So the first, the electronegativity of nearby atoms. And this effect of an electronegative substituent falls off quickly with distance. But the presence of an electronegative atom or group reduces the electron density on atoms bonded to it and therefore the shielding. So this effect deshields nearby nuclei and causes them to resonate further downfield, that is, with a larger chemical shift. Now the next dependence is on the hybridization of adjacent atoms. So one example of this is that vinylic hydrogens are more deshielded than alkyl hydrogen. This explanation lies in the hybridization of carbon. Now because sigma bonding orbitals of an sp2 hybridized carbons has more S character than a sigma bonding orbital of an sp3 hybridized carbon. Now sp2 hybridized carbons, those are more electronegative, and so vinylic hydrogens are deshielded by this electronegativity effect, and their nuclei resonate farther downfield rather than or relative to alkyl hydrogens. And then finally, the diamagnetic effects from pi bonds. So when molecules contain double or triple bonds here, the effect is a little bit different than the sigma bond electron density that we talked about earlier. So the applied magnetic field induces a circulation of the pi electrons, which in turn produces an induced magnetic field. Now the difference here, for example, between acetylenic hydrogens and vinylic hydrogens, and so that corresponds to, for example, the pi electrons in a triple versus a double bond, respectively, is based on the geometry. So given the geometry of an alkyne, triple bond, remember, and the cylindrical nature of its pi electron cloud, the induced magnetic field is shielding in the vicinity of the acetylenic hydrogen. Therefore, lower frequency electromagnetic radiation is required to make an acetylenic hydrogen nucleus resonate. So the local magnetic field induced in the pi bonds shifts the signal of acetylenic hydrogen upfield to a smaller chemical shift value. Now, the effect of the induced circulation of pi electrons in a vinylic hydrogen is opposite to that. So the direction of the induced magnetic field in the pi bond of a carbon-carbon double bond instead of a triple bond is parallel to the applied magnetic field in the region of those hydrogens. So the induced magnetic field deshields the vinylic hydrogens and thus shifts their signal downfield to a larger chemical shift value. Now the effects of the pi electrons in benzene or other aromatic molecules are even more dramatic than in the alkenes or alkynes. So the aryl hydrogens absorb even farther downfield than the vinylic hydrogens. And so, again, you can refer back to your correlation charts. And this is accounted for by the existence of a ring current. So an applied magnetic field causes the pi electrons of the aromatic ring to circulate, giving rise to the so-called ring current and an associated magnetic field that opposes the applied field in the middle of the ring, but reinforces the applied field on the outside of the ring. Thus, given the position of aromatic hydrogens relative to the induced ring current, they are deshielded and come into resonance at a larger chemical shift.